Welcome to homework.
Hello everyone, today we're doing chapter 23, problem 48, and this problem asks us to synthesize each of these following compounds from diethyl malonate. And you can use any organic or any inorganic reagent. So let's start with A. So we see that we have this carboxylic acid, which we can form malonic ester synthesis, and then obviously the carbon adjacent to that is going to be the alpha carbon. So we have this alpha carbon here, and to that we're adding 5 carbons, and not only that, we're adding 5 cyclical carbons. So we've done a problem in the past in the textbook in this chapter that we've added cyclical groups, and the only kind of different thing is that instead of having your Rx group, it needs to be XRX, meaning that there needs to be a leading group on either side such that it allows for intramolecular cyclization to occur. So let's do A, see what I'm talking about. So in the beginning of A, we see that we have our starting material, and we're going to react that with a strong base to deprotonate the alpha position to make a strong nucleophile at the alpha position. And then secondly, we're going to add our alkyl halide being 5 carbons long, but then we're going to have 2 halides on either side. So we can have bromine on both sides, for example, and have 1, 2, 3, 4, 5 carbons in between them, another bromine. So then we'd see that the product of this reaction would be 1, 2, 3, 4, 5 with bromine. And now, if I add a second equivalent of just the strong base, that's going to deprotonate again the second alpha position, or the second proton at the alpha position, making a strong nucleophile. And the nucleophile will right away find this electrophile that's very close to it and do an SN2 nucleophilic backside 180-degree attack, and therefore is going to form a cyclical structure. So you can imagine that your nucleophile is going to be very close to your electrophile, which happen to be on the same molecule, so you'll have an intramolecular cyclization occurring to form a 6-membered ring. You have 1, 2, 3, 4, 5, 6 carbons, so a 6-membered ring. Then you add acid conditions to have acid hydrolysis and spontaneous decarboxylation of one of these carboxyl groups to form your final product for A. So now B, it actually builds off of A. So instead of having a carboxylic acid, we just have an alcohol. So we're reducing this acid all the way to an alcohol. So for B, you take the product of A, and then you react that with the reducing agents, for example, lithium, aluminum hydride, and water. And you're going to reduce this carboxylic acid to an alcohol, to a primary alcohol. So you now reduce this acid to a primary alcohol to give you B. Now in A, what we're doing is we're building off from, in C, what we're doing is we're again building off from A, but now we're adding 2 more carbons and we're reducing the acid into an alcohol. So what we can do is we can do Fischer's esterification used from A. So in C, we'll start with A and then we'll do acid catalyzed Fischer's esterification. So we want to add one of these carbons. So we'll have methanol, so MEOH, with some sort of acid, so H2SO4. So now we have Fischer's esterification. So now we're esterifying this carboxylic acid. So we're going to be left with now a carboxylic acid, or an ester now with 1 extra bond here. And now from here, what you can do is we can actually have some sort of like Grignard reagents. So we can add a Grignard reagent that's going to act as a nucleophile. So we'll have a carbanion that's going to attack the electrophilic carbonyl carbon here, ester carbon here, and then we would form a new carbon bond and get rid of this ester group here. So then if we do that one time, so if we add, for example, magnesium bromide with a methyl group on it, so it's a Grignard reagent, and water, we would have essentially a carbanion. So this is equal to saying we're going to have just like a CH3 minus. That's going to act as a nucleophile to attack this electrophilic carbon here. So then you kick off the methanol that you just added, and you now have a carbon bond. And now if you do this one more time, there's no leaving group the second time you do this. So now, because there's no leaving group this time, there's no methoxide that can just happily fall off. Because there's no leaving group, once you do this again, you're actually going to form that carbanion again. But now because there's no leaving group, the carbonyl is just going to go up and is just going to stay as an alcohol. You're not going to collapse that carbonyl back down to reform the carbonyl. You're just going to keep it as an alcohol. So then that's going to yield you your product in C, which is now you're going to have that extra carbon bond here, but then you're going to have that alcohol also coming out like this. So the only reason that this worked is because we first had to esterify it to make a good leaving group. So now that we have a good leaving group, oxygen being electronegative is happy to accept these 2 electrons in the sigma bond. So now when that carbanion attacked this carbonyl group, the carbonyl went up and back down, and then it kicked off a good leaving group being this methoxy. But now once it was gone, there's no more leaving group to kick off, so then that's how we get product C. And now in D, a very similar thing has to happen. So we need to add an ethyl group here now to form an ester. So in D, once again, very similar to in C. So for D, we're going to take a product of A, and now we're going to esterify it, but with an ethyl group this time, ETOH, so ethanol, with our acid. And now we added an ethyl ester. But now we need to add a carbon at the alpha position. So what we need to use is a strong base. So we can use LDA, for example, as a strong base to deprotonate this alpha proton here to make a carbanion that's going to act as our nucleophile to attack an alkyl halide being 1 carbon long with any halide. So let's do bromine, for example, and then we'll get our final product for D with this methyl group added, and then this ester group attached as well.